morning, good afternoon, or good evening to our dearest professor. We are the group number 3 and I am Martin King Florence Paul R. Alongside with my co-researchers De Leon Tristan Joshua D, Dokila Sofia Lara R, Hippolito Rafael M, and Villegas Eunice SLP. We'll be presenting our research entitled Integration of AI and IoT-based monitoring on efficiency and reliability of smart grids. Despite the growing integration of artificial intelligence and Internet of Things in smart grid modernization, our research identified several key gaps that limit large-scale development and efficiency. First, there are only limited studies that explore how AI and IoT integration specifically improves the efficiency, monitoring, and control of renewable energy systems. Secondly, existing research highlights challenges like cybersecurity, data privacy, and interoperability, but lacks practical evaluation within actual smart grid infrastructures. Lastly, there is still no comprehensive and scalable AI to IoT framework designed for suitable and reliable energy management. These gaps guided the development of our study statement of the problem, which focuses on three main questions: how AI and IoT integration enhances renewable energy systems, what challenges and limitations arises in its implementation, and lastly, why is it important to develop a secure and sustainable AI to IoT model for renewable energy management. Through these questions, our research aims to address the existing gaps and contribute to building smarter, more efficient, and more sustainable energy systems.
Now, let's move on to Chapter 2, Review of Related Literature for our study on AI IoT in smart grids. For this, I'll start with an overview of why IoT matters for modern power systems, then review key studies and theories, and finish by identifying the main gaps and recommended directions for future research. Global demand for power is increasing, while traditional grids cannot keep pace. Thus, researchers and utilities have started to look at IoT, enabled smart grids as a solution. Smart grids are equipped with sensors, smart meters, and networks which allow for real-time monitoring, two-way communication, and automatic control between utilities and consumers. Technologies that are commonly mentioned are RFID, wireless sensor networks, cloud platforms, and 5G. While IoT has significant benefits in terms of efficiencies and reliability, studies continue to highlight important issues such as cybersecurity, data privacy cost, and poor interoperability. Now that we have the big picture, I'll explain how IoT is architected and where it's applied across the energy value chain. Most studies treat IoT in smart grids as 3-layer or 4-layer architectures. These include perception or sensors, network or communication, middleware or aggregation, and application or services and control functions. The layers can support the various steps from data collection to decision making. Practically, IoT is applied to every area: renewable integration in generation, fault detection in transmission, load shedding and smart metering in distribution, and consumer automation and EV charging at the consumer end. Despite this versatility, the problems remain the same in part: system heterogeneity, limited device reliability, weaknesses in cybersecurity, and overall the very large size of databases to be stored and processed. With architectures and applications in mind, next, I'll show how frameworks assess and guide smart grid development. One major trend is the intersection of AI with IoT, named AIoT. AIoT can provide predictive maintenance, reliable forecast of load, anomaly detection, and real-time optimization of renewable resources. Various papers demonstrate methodologies such as LSTM for forecasting and model predictive control for shifting of variable generation to solve the problems of privacy and scalability. Researchers propose an approach of edge computing and federated learning to enhance trust, and the techniques based on blockchains are studied. The literature also highlights green IoT designs, energy harvesting sensors, and dual battery devices, which reduce dependence on maintenance-intensive batteries. I'll now summarize the principal theoretical frameworks that underpin these findings. Our review identified 5 core concepts that the field builds upon. First, SGAM for interoperability and structured system design. Second, multi-layer IoT architectures to organize sensing through application. Third, AI-driven analytics for predictive and prescriptive control. Fourth, multi-agent systems, also known as MAS, for decentralized coordination among devices. And lastly, green IoT, emphasizing energy efficient, sustainable device system. Together, these frameworks explain how systems are structured, analyzed, and controlled in the literature. Having established what the literature support, I'll discuss where the literature falls short, the gaps, and controversies. In conclusion, IoT and AI will play an important role in improved efficiency, reliability, and integration of renewables within contemporary grids. It has been determined within the literature that future research should take particular note of the following priority areas: the development of common interoperability frameworks, lightweight, secure, and communication protocols, the building of energy efficient IoT hardware and software, improved multi-agent coordination methods, and sound data governance and privacy strategies. These priorities will assist to make the structures of AI IoT smart grids secure, scalable, and sustainable. That concludes our chapter 2. Thank you for attention.
A pleasant afternoon, everyone. My name is Christian Joshua Digi De Leon, and I am here to present the Chapter 3 of this research, also known as the methodology. For our research design, we use descriptive correlational quantitative research design because we're aiming to find the relationship of two variables. That variables are the AI and IoT-based monitoring and the renewable energy-based smart grid systems. For our data collection method, we use a G-forms with a set of questionnaires that will be answered from agree to disagree. For our sample selections, we use a purposive sampling. It consists of 35 students from BSEE1C. We use these students because they're from electrical engineering. And lastly, for our data analysis technique, survey responses from Google Forms will be downloaded into a spreadsheet and analyzed. Descriptive statistics will be applied to the prepared data, specifically tables. The results of descriptive analysis will be presented in tables. The frequency tables will give the number of responses and the percentage for each response selected by the subjects.
Good day, everyone. I'll be presenting the chapter 4 of our study, which focuses on the results and findings gathered from our survey about the integration of IoT-based monitoring on the efficiency and reliability of smart grids. The table shows that the most of our respondents were male, comprising 60% of the total. The majority of the participants were between 18 and 20 years old, which represent 94% of the sample. This reflects that the most of our participants were first-year electrical engineering students. For the first category, efficiency and monitoring, the grand mean was 4.10, the highest among all categories. Respondents strongly agreed that the AI and IoT integration enhances energy efficiency through real-time monitoring, accurate power prediction, and automatic balancing of electricity supply and demand. The second category focused on infrastructure, scale, and data challenges, which obtained a grand mean of 3.74. This suggests that while respondents recognize the benefits of AI IoT integration, they also see challenges such as high implementation costs, complex data management, and the need for scalable systems. The third category, which is the reliability, sustainability, and operational impact, achieve a grand mean of 4.05. This means the respondents agreed that AI IoT integration enhances predictive maintenance, supports sustainability, and help improve decision making in renewable energy systems. For the last category, which is security, policy, and resilience, the grand mean was 3.99. Respondents strongly agree that cybersecurity and government policies are crucial for protecting and implementing AI IoT smart grid system effectively. Next is support for research questions or hypotheses. The results support our research assumption that AI and IoT integration greatly improves the efficiency, reliability, and resiliency of smart grids. IoT provides continuous data monitoring, while AI enables intelligent decision making, predictive maintenance, and optimization of energy use. Next is the comparison with existing literature. Our findings align with previous studies by Kermani et al. And Tabasum et al., which also highlighted how IoT improves energy efficiency and system reliability. Similarly, our respondents agree that AI and IoT integration enhances monitoring and sustainability. However, the challenges mentioned, such as cost and data management, are consistent with Cabalchi et al., who noted this as barriers to implementation. Overall, this shows that our results support existing literature while reinforcing that AI IoT systems are beneficial but still face real-world limitations. Lastly is the implications and limitations of the study. The study's findings offer valuable implications for school, companies, and policymakers. However, the results were limited to the student perceptions and not real operational system. Future researchers should test these findings through field studies and larger samples.
Our first research question examined how AI IoT technologies enhance renewable energy systems. The data revealed strong student support, with responses averaging 4.1 out of 5. Participants recognized three critical capabilities. First, IoT sensors provide uninterrupted monitoring of generation and grid conditions. Second, AI model can forecast power output from variable sources such as solar and wind. Third, smart systems autonomously redistribute electricity to match consumption patterns. These findings validate that students understand the operational advantages these technologies bring to energy management. The second question addressed implementation barriers, receiving a grand mean of 3.74, indicating moderate agreement. Respondents acknowledge four significant obstacles. First, financial constraints represent a major hurdle, as deploying these systems requires substantial upfront investment. Second, technical complexity increases rather than simplifies operations, particularly in data management. Third, different manufacturers' devices often struggle to communicate effectively, creating problems in terms of integration. Lastly, the infrastructure itself consumes considerable power, which somewhat contradicts sustainability goals. Despite recognizing these problems, students still viewed the technology favorably. Our third question explored why secure, scalable, and sustainable models matter. The results span three categories, with grand means between 3.74 and 4.05, all showing agreement. Question 9, specifically about scalability, scored 3.94, demonstrating student awareness that systems must accommodate growth in device numbers and data volumes. The high scores across security, reliability, and sustainability categories confirms that students don't view these as optional features, but rather as fundamental requirements. This reflects a mature understanding that technical performance alone isn't sufficient. Systems must also be protected, expandable, and environmentally responsible. To conclude, we confirm that AI and IoT integration shows strong potential for improving our electrical grids, with efficiency rating reaching 4.1 among our participants. We also identified and measured the main challenges that needed to be addressed, particularly in areas like infrastructure costs and system compatibility. Most importantly, our work contributes to the global shift towards sustainable energy systems by highlighting both the opportunities and the obstacles we face. The smart grid we studied are not just concepts in a paper. They represent the future of how we generate, distribute, and manage electricity. Understanding both their promise and their limitations is the first step toward making them a reality. That is all. Thank you for listening.